Okay, this is the problem-solving part of the lecture. Now, these examples here are somewhat similar to the ones we're doing towards the end of the theory part of the lecture. So, they're all of the same format. You're given a set, you're given an operator, and you're asked to see whether, for each example, whether the operator here is a legitimate, well-defined and closed binary operator on that set. Okay, that's the setup, that's the format. All right, how about this one? So the set is the integers, and the the operator is the multiplication. So if you take any two integers and you multiply them, you will get a unique answer, right? One and only one answer. And that answer belongs to the integers, right? The answer will be an integer. So that one's okay. That's well defined. Okay. And the result, if you take any two integers, multiply them, you'll get a unique result. Just one result, one and only one result. And the result belongs to the integers. So these two conditions are satisfied, conditions for a binary operation. So that pair, this set, this operator, that's a binary operation in the sense of textbook users. All right, how about this one? The set now is the natural numbers, and the binary operator is this kind of diamond. So A binary operator, A operator B is defined to be a natural number, to the power of another natural number. So A to the power B. Now, is that well defined? Is it closed? Do you get a unique result, A to the B? Yeah, that's unique. One and only one result. And now A to the B. If A and B are both natural numbers. Now, by natural numbers, meaning the counting numbers, right? 1, 2, 3, 4. So the positive integers, if you like, the natural numbers. So this result, if you raise a natural number by a natural number, you'll get another natural number. So it's close. So this one looks to be okay. Right, third one. The set now is a set of reals. The operator is division, divide. And now, division, so you have to take two elements. Is that, can you get a result for all cases? Well, if your binary operator, so it's A, if it's something like this, but if B is not, you've got a problem. You're dividing by 0, so that doesn't work. So it's you don't have a result for all possible cases, all possible ordered pairs, A and B. So this one fails, okay? Because it's just not defined when B is 0. That's like a counterexample. Oh, how about this one? So your set is the set of all integers. The binary operator is this power, so A is to B. Do you have a problem there? Can you find an example where it fails? So it's of the form A to the B, and the result has to be an integer. Well, try this. A is 2 and B is -1. Right? Now it's a set of integers. Right? So the set of integers is 0, plus or minus 1, plus or minus 2, and so on. So your integer could be negative. Okay? Now it's this diamond operator, which is a power operator, A to the power B. But if B's -1, then look what you get. You get 2 to the power -1. Now that's just a half, right? Now a half is not an integer. Okay. So we found a case where this doesn't work. So the binary operation isn't closed for all ordered pairs. So this fails. Okay, that doesn't work. How about this one? The set is again the integers. The binary operator, well, it just it takes all possible pairs, ordered pairs, and the result for each ordered pair is the first element. So A operator B is just A. Okay. Now, is that well defined? Is that closed? Well, A certainly belongs to the set because here it is again, and there's one and only one result for each pair. So these two conditions are satisfied. So that's okay. Okay? That's all right. The two conditions are satisfied for it to be a legitimate binary operation. Now, how about this one? Now, this is similar to this one, in fact. Okay? We could create a table here. So let's do it quickly. I'll do it again quickly. And is it? You know, when we look at the table, each result, each member, each C, if you like, each result, does it belong to your set? Now your set is 4 integers, 1, 3, 5, 7. So let's actually, and the binary operation is the same as here. So it's just the product mod 10. You know, you probably can't see the 10. It's probably a bit small here, but it's the same as this. Okay. So take your ordered pair, multiply them, and then mod by 10. So let's actually draw the table. So I'll do this rather quickly. 1, 3, 5, 7. Those are the 4 elements of your set. 1, 3, 5, 7. And then you multiply the two of them. You take an ordered pair, multiply those two numbers in the pair, mod by 10, get the result, and put that in the table position. Okay, 1 by 1 mod is just 1 by 3, 5, 7. So, okay, 3 by 1, 3. 3 is 9. Whoa. Well, it doesn't work. That's a surprise. Huh. Okay, 9 is not a member of your set, so it fails. Right? Didn't expect that. All right. Okay. How about this one? The reals. Your set is the reals. The binary operator just gives you the answer 0. Right? Now that's a result, and it's for each pair. You know, it's one and only one result, so that's okay. Now, is it closed? Like, is the operation closed? Now 0, that's a real, right? Belongs to R, so that's okay. Now, how about this one? Your set now is the set of all complex numbers, C. Your binary operation is the modulus, your mod, the absolute value, like the mod of -4 is 4. The mod of -8 is 8. Just the absolute value. So the operation is to take the difference between these two and get the absolute value. Now, is that okay? I mean, you got a unique result, right? I mean, so if A and B are just complex numbers, you get the difference of those two complex numbers and then mod it. I assume you know some complex number theory. You know how to find the absolute value of a complex number, right? So it's well defined, and it'll give you a real number, but real numbers belong to the complex numbers, so that should be all right. So let's say that's okay. All right. In this case, the set is all matrices. the set of all matrices. And the operator is matrix multiplication. Now is that well defined? Is that closed? Well, what happens if you take two matrices that are incompatible? Like, say you have one matrix and its form is a 2 by 3 matrix, and the other one that you take is like a 4 by 5 matrix. Well, you can't even multiply those two, right? To be able to multiply them, this number and this number have to be the same. So if this were a 4, that would be defined. Then you could multiply the matrix, right? And you would get a matrix, and therefore it would be closed. But this set here is any matrix. So in general, that's going to fail, because you can't even multiply two general matrices, because you won't have this number and this number, you know, what is it, the rows, this number of columns, so there's a number of rows in the second matrix. If this number and this number are not the same, you can't even multiply the two matrices. The multiplication is not even defined, right? So there's just no result. So in general, that fails. Now, what about this one? So now we're being more specific about the set of matrices. They are 2 by 2, you know, 2 rows, 2 columns. These are 2 by 2 matrices, and the operation is we're trying, you know, all these x that we're trying to determine whether you have a legitimate, well-defined binary operation. So, you know, with these two conditions. So the operation now is defined as the determinant of the difference between the two matrices. So I assume you know how to subtract two matrices of the same size. They're both 2 by 2. And you then find the determinant of that difference. Now, a determinant is just a number, right? Just a real, usually. And a real number is not a matrix. So this number does not belong to that set, the original set. And the original set is the set of 2 by 2 matrices. So this is wildly wrong. Right? It's not close. Now this last one, a little subtle. Now it's the operator is like the diamond again. That's this one. So it's a number raised to a power, and those numbers are now reals. So you've got something of the form a to the b, and the a and b are now reals. Now, can you think of a counter example? No. When I was going through them, I found this one to be the most subtle. Well, let's play devil's advocate. Imagine it fails. Okay, so try to find numbers a and b where this operator is not closed. Okay, not closed. What does that mean in this context? Well, it means the result does not belong to the real numbers. Okay? Well, if the result is not real, so a and b are real numbers, right? So we're talking about numbers. But if the result is not real, what kind of number could it be? Well, it could be a complex number, right? That's not, a complex number is not real. I mean, it can be, but you know, there are cases where it's not. So let's try to find a case where it's not. So let's try to find a and b so that we get a complex number. All right? How about this? A is -1 and b is 1/2. Well then, so you plug those in and you get a square root of -1. That's I. Okay? Now I, very definitely, is not a real number. It's a complex number. So we've found an ordered pair, a and b, so -1 and 1/2, that give you a non-real result, a complex number result. So that failed. Okay? Right, that's it. So for next lecture, lecture 4, will be on integers. And then lecture 5 will be on groups. So we finally get round to what this lecture course is about, which is group theory, and it's a bit longer than normal, lecture 5. So see you again for lecture 4. Ciao.